Alright, in this last video in section 12.5, we're going to look at problem number 5, which is on what's called the golden ratio. And this says that if the ratio of two quantities equals the ratio of their sum to the larger of the two quantities, they are in the golden proportion, also known as the golden ratio. And see this figure below. Okay, so to translate what they're saying here, let's say we have a line segment here, and if I'm going to divide this line segment in such a way that the long piece to the short piece are in the golden proportion, then the following has to be satisfied. So let's say I cut the segment right here, and I'll call the long piece A and the short piece B. Then in order for the long to the short to be in what we're calling the golden proportion or golden ratio, we're going to take the long piece divided by the short piece, and that's going to have to come out to equal the ratio of the entire line segment, which has length A plus B, divided by the long piece. Okay, this is the condition for the long to the short to be in this special golden ratio. Okay, and so reading in the problem, it says translate the above quotation into an equation involving A and B. Well, that's exactly what we just did here. So now for part B, it says it's common to write the common ratio in the above, that's poor wording, in the above equation as this, it's a Greek letter phi. And this ratio, by the way, does go back to the ancient Greeks. And so we're going to call what? The common ratio of long to short, we're going to call it this Greek letter phi. And then it says to rewrite your equation in part A in terms of phi alone, then solve the equation for phi. Okay, so this ratio, this thing right here, is what's referred to as the golden ratio. And what we're going to do in this part of the problem is find the numerical value of the golden ratio. So how can we go about doing that? Well, let's take this equation up here and let's break this down a little bit. So on the right hand side, I'm going to go ahead and split that fraction up into two pieces. I have an A over an A, and I have a B over an A. And so I have A over A plus B over A. Okay, and now notice A over A is just 1. So this is equivalent to saying A over B is 1 plus B over A. All right, and now, right, what do we know? Well, what are we calling this ratio, A to B, the long piece to the short piece? That's just phi. So on the left here, I can replace where I see the A over B with this special Greek symbol phi. And so then what am I going to get over on the right? I have 1 plus, and then I have B over A. And notice, this is kind of the big key insight here, is that if phi is A over B, okay, then what is B over A? Well, B over A is the reciprocal of A over B. So put another way, right, if I flip this fraction over to get B over A, I'm going to have to flip this symbol over here over on the left side. So that's going to be 1 over the golden ratio phi. And so I'm going to replace that here. Okay, now of course, still somewhat maybe a little weird looking, but the benefit now is that, well, we only have one variable in here, right? One unknown. And so now what I can do is go ahead and solve this equation. The LCD of this equation, well, there's only one denominator, and that's this Greek letter phi. So what I can do now is just multiply both sides by this LCD, and that's going to leave us with phi times itself, which is phi squared. And over on the right side, I'm going to distribute the phi here and here to give us phi plus, and 1 over phi times phi, those would cancel out, and I'm just going to get 1. Okay, so this is a quadratic equation. So I'm going to go ahead now and subtract both phi and 1 from both sides. And so that's going to give us this equation that phi squared minus phi minus 1 is equal to 0. Okay, so this is a quadratic equation, and I can go ahead and label the coefficients as a equals 1. B here, the coefficient of phi, would be negative 1. And then my c value would be negative 1. Okay. All right, so now let's go ahead and solve this using the quadratic formula. And this is really the first time the quadratic formula has appeared in this class, and we will definitely spend a lot more time with the quadratic formula and review it in a lot of detail a little bit later on in the quarter when we talk about quadratics in more detail. But for the moment, let's go ahead and just apply what it says. So remember, the quadratic formula looks like this. It says x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, to solve quadratic like this, we can just simply plug in our coefficients into this right-hand side and we'll get our solution. So let's do that here. I'm going to take the opposite of b plus or minus the square root of b squared minus 4 times a times c, and then divide all of that by 2a. So I'll go ahead and fill in. Again, we're taking the opposite of b, and then I have a b squared right there. And then my a here is 1, and that goes there and there. And then lastly, we have our c, which goes right there. Okay, so now let's go ahead and simplify this a little bit. The opposite of negative 1 is 1, plus or minus the square root of, and inside I have negative 1 squared, well that's a 1, and then minus 4 times 1 times negative 1, that's a plus 4, because a negative times a negative. So all together it's 1 and 4, that's 5. And then I have in the denominator 2 times 1, so that's 2. And notice there's really two numbers here. There's the 1 plus the square root of 5 divided by 2, which if you use your calculator is about 1.618 roughly. And if I use the minus sign, 1 minus the square root of 5 over 2, okay, this comes out to be about negative 0.618. But remember, what is this quantity, this Greek letter phi thing standing for? It's standing for the ratio of the long piece of a line segment to the short piece. So it doesn't make sense that that ratio would come out to be a negative number. Okay, so in fact, the golden ratio is this number right here. It's the 1 plus the square root of 5 all over 2. And again, I said, this number goes back to the ancient Greeks. They, at least some of them, held this number in almost a mystical regard, and it was used, and still is used, in a lot of different areas, architecture, art, certainly in math. It shows up in a lot of interesting places in nature, like looking at like the face of a sunflower. I mean, arms of the Milky Way galaxy. It seems to sort of crop up in all kinds of interesting places. Also, like the dimensions of a lot of screens, like iPhones, TVs. The ratio of the long to the short side tend to be roughly in this ratio. So it's interesting problem, interesting history. But as we see here, it's also an illustration of how these rational equations can be used. Okay, well, that's going to do it for section 12.5, and that'll do it also for the rational equations or the rational expressions material. So I'll see you next time. Thanks.